welcome you into another statistical topic. Of course, today our focus is going to be on diagnostics for simple linear regression. Before I get started, I think I'm actually going to go retrospective, like how do we find ourselves in this topic? Okay, you need to be able to understand how we find ourselves in this topic for you to be able to understand the topic. Of course, we started by trying to characterize relationship between two variables, one dependent and one independent. And I told you the other time that if you want to do that, we need to first specify our model, which I showed you last week, how we can, where I walk you through specification of linear regression. You saw population regression. You saw fitted regression model, and I also walk you through how to estimate parameters in the linear regression model. I remember I walk you through an example in a factory production where we look at the relationship between the production size and the runs time. Of course, my TA has also walked you through how to implement that in R. But you know what? Well, what do we want to do today? When we estimate parameters in a linear regression model, how do we actually know whether the model will do a good job? I'm going to say that again. How can we be sure whether the regression model we specified, whether it's going to do a good job? And the only thing to know is to perform what I call diagnostics. So what do I mean by diagnostics? Is evaluating our model. Okay, we basically want to see whether the model is fantastic, and that is the reason why I'm actually going to walk you through assessing conditions. Let me tell you this. Every statistical model has assumptions. A model is as good as assumptions put into a model. If assumptions in a model are not met, then your model is not going to do a great job. And that is the reason why at times it's going to look as if our models are failing us. Our models are not failing us. But do we bother to test whether assumptions underlying the use of a model hold? So uh, if we want to assess conditions, if we want to test assumptions, we actually use what I call residual plots. Okay, I'm actually going to walk you through how to use residual plots to navigate doing that. Then I'm also going to walk you through some unusual observations. Some usual observations in data, okay, may actually change the trajectory of decision. Like, it's part of the assumptions that need to to be investigated. Okay, whether we have some outlying observations, some observations that are not consistent with the rest, because they could be problematic as well. Okay, so I want to welcome you to assessing conditions, which is more or less like we are subjecting our model to diagnostic testing. Now, maybe you run a regression model, just like you have these results. Of course, my TA walk you through how to use an R software to implement linear regression in R. If you run a simple linear regression model in R and you get these results. Now, the question now is, what will you conclude based on the model summary? Is this simple linear regression model a good fit to the data? What is the essence of using a model? The essence of using a model is basically to capture reality. I told you the other time. How do I know my model has done a great job? And that is why we need to investigate whether assumptions underlying the use of the model hold. Okay, now for instance, I'm actually going to show you this. Let's say you have four sets of data. You have a data set one, data set 2, data set 3, data set 4. And you in each data set, you have two variables, X and Y. And if we want to specify a model in statistics, we use the principle of subjectivism. What do I mean by that? Subjectivism. Okay? Subjectivism. When I say the principle of subjectivism, maybe based on our experience, we specify model based on our experience. That's what I mean by the principle of subjectivism. Okay? Based on our experience. Okay? Now, I'm going to write the subjectivism now. So that's what I mean. Okay? That's what I mean. Subjectivism. Okay? Now, take a look at this. I got 4 different kind of data sets. They are bivariate in nature. X and Y. We got dependent, we got independent. I needed to take a look at the data set 1. When I generate a scatter plot for data set 1, that's what I got. That's looking like a straight line, even though we don't have all the points on the line. I told you the other time. We can, even if it is not until you have all the data point on a line that you can say you are using simple linear regression. Okay, don't forget some point will be deviated away. That's why it's called a scatter plot. Take a look at data set 2. That's the curve. Take a look at data set 3. Even though we got a straight line, but we got a point that is not outline. That is not consistent with the rest. That we can actually suspect as an outlier. If you take a look at data set 4, even though that particular data point is on the same line with them, but it's far away from them, that we may be calling high leverage. If you take a look at this, we don't just specify model, but before we specify linear regression model to data, then it means we've already generated a scatter plot. The scatter plot will give you the sense of the model you're going to specify. Now, what you can see for data set 1, it is reasonable to specify linear regression for data set 1. For data set 2, it is not reasonable because that is not a straight line, that's a curve. So which means you're actually going to think beyond a linear regression. You could, consider other form of a non-linear model that we're also going to do in this course. If you take a look at the data set 3, even though linearity assumption hold, but there is a presence of an unusual observation. If you look at data set 3 and data set 4, okay, there's a point that is not consistent with the rest. According to Benkamp in 1982, he defined an outlier as a data point that is not consistent with the rest. And there is possibility that this particular point, okay, could be problematic to the model if it is not being investigated. Okay, now let me just tell you, I work my area of a PhD. I actually work in this area. The title of my work was the development of the exponentiated F distribution in the to be used in analysis of variance when there's a violation of assumption. Okay, when there's a problem like this, how do we actually address that using the parametric framework? Of course, when there's a problem like this, of course, there could be different approaches. In statistics, we have the parametric, we have the non-parametric. Some could actually resort to non-parametric means of seeking redress. But what I just wanted to understand here is when you are working with data set and you are seeking a relationship, before you go ahead and specify your model, you need to first generate your scatter plots. The scatter plots will give you the sense of what model can you specify. Now, so what causes issues in the model fitting? There are two things that causes issues in module fitting. Number one, module assumptions violations. I remember last week I walked you through, specifically on Friday, I walked you through assumptions of linearity, assumptions of normality, assumptions of constant variance, independence of the error. If any of those assumptions is violated, then there's going to be issue in your model, which means we cannot trust your model. When you use any recommendation from your model in policy formulation, you're actually going to regret that. Okay, then another another thing that causes issue in model fitting is an unusual observation. If you take a look at the two, model assumption violated is different from unusual observations. You can see that? You know, some researchers are going to argue this. Oh, because I've already investigated assumptions, I don't need to investigate whether there's an unusual observation. If you don't do that, then you cannot trust your model. You're basically going to address model, you're going to investigate model assumptions. You're also going to investigate whether there's an unusual observations. Now, I want to focus on data set one now. Now, this is what happened. And I need you to pay attention. If you don't understand what I'm presenting, please ask questions. There's something that we do before we go into research that I'm actually going to call preliminary step. Preliminary. Okay? Preliminary. What you do on a preliminary stage, when you are seeking to investigate relationship between two variables, is to generate a scatter plot. That is the first thing you're going to do. After you have generated your scatter plot, and you can say something like, oh, this is more or less looking linear. Okay, then you can now go ahead with module estimation. Okay, where you're going to obtain your beta null, your beta 1, but let me tell you, there is something more to do. Now, there's something more to do is what we call, we call that a post-analysis. The post-analysis is where the residual analysis is going to come in. The residual analysis is going to say, okay, even though I know from day one that the relationship is going to look linear, I also need to confirm that conducting another analysis that I'm actually that we call residual analysis. Now let me tell you now, what you are saying on the other end is called residual plots. Okay, now what do we use residual plot to do? You only get residual plot after you have already estimated parameters in your model. Okay, now if you look at the residual plot, if the residual plot do not follow pattern, okay, no pattern. If there is no pattern, okay, then you have already justified linear. But what if it shows pattern? If your residual plot show pattern, then it actually means linearity assumption is violated. So the only way, which means if I'm trying to characterize relationship between two variables and I generate a scatter plot and the scatter plot look like that, then the residual plot should look like that. The residual plot should show no pattern, no trend. Does that make sense? And what that actually is trying to talk about is that, oh, you know what? The linearity assumption holds. Now, the next thing that I actually want to talk about is let us now see. The other time I show you different kind of plots, right? Like if you are using 4 different data set, okay, and you have the scatter plots for data set 1, 2 up to 4 like that, okay, we now want to see how the residual plot will look like. For data set 1, you can see the corresponding residual plots. For data set 2, the residual plot, we also have para. So if you take a look at the data set 3, data set 4, data set 2, 3, and 4, there's a violations. Okay, like I said, the scatter plot is part of the preliminary step in module fitting. While the residual plot, is the plot that you generate after you have already estimated parameters in your model, is part of diagnostic procedure. Let me tell you this. This is a patient. Visit my clinic. Before I start, treating this patient, I conducted a test, right? To know the level of intervention. After I have succeeded in treating this patient, I still need to run another test to be able to confirm whether I've succeeded in doing that. That's what we're doing here. Scatter plots. Lastly, residual plots. Does that make sense to everyone? Okay. Now, if you take a look at the assignment that I gave currently, where I wanted to use the rate my professor data. If you go to online, every professor is actually being rated by their student. They rate the professors based on some variables, quality, clarity, and so on like that. Okay. Now take a look at these two variables where you are working with two variables. When you look at the relationship between the quality and the clarity of a professor, we want to be able to see, if I know the clarity of a professor, can I actually predict the quality? When I say quality, what do I mean? The quality of teaching. Does that make sense now? Okay. Now, with the data set now, the observation would be that would be the number of students that rate the professors. Okay. Now, we plotted that. We got a scatter plot. You can see that's a straight line, right? That's a scatter plot. What would be the corresponding residual plot? The residual plot is going to look that way. I know on Friday my TA walk you through now how to generate residual plots. So take a look at that. Okay, so what we are trying to tell the world here is that the linearity assumption hold. Okay, the scatter plot actually show a straight line, and the residual plot show no para. Now, what are these assumptions again? Don't forget, the assumption revolve around the error terms, right? Around the error. And the assumptions are linearity, independence, normality, equal variance. I think I walk you through that the other time. Okay, now, do you know in exam, I can actually give you something, something like this. Give me 1 second. I can give you something like this in exam. But what if you're giving, maybe I give you a residual plot like that, and I ask you, what are the assumptions that are violated? But before I can ask you that, residual plots can only be used to investigate two of the assumptions. What are these assumptions? Even though we have four assumptions, residual plot can only be used for two. One, linearity, okay? And two, constant variance. Does that make sense to you now? If you take a look at that linearity, of course, the residual plot here does not show any pattern. Because of that, I'm going to say linearity assumption holds. Now, when you're talking about equal variance, what do I mean by equal variance? I'm talking about when you look at the residual is on the y-axis, and your independent variable is on the x-axis. Now you're going to see that the variance of the residual, it remains the same when you increase from the values of one x to the other. Like if you take a look at that, they are equally dispersed. That's what I mean. Okay, that with what you are seeing now, okay, that is talking about constant variance. But you know what? Assumptions of normality, assumptions of independence, we cannot use residual plots to investigate that. So the residual plot can only be used to investigate assumptions of linearity and assumptions of equivariance. Now take a look at this. This is a situation where the constant variance assumption is violated. You can see from 0 to 1, the points are clustered, right? But when you take a look from 2 to 4, they are dispersed. Take a look at it. That means the constant assumption, the constant variance assumption here is violated. Take a look at that. And that's exactly what I mean. So that violates the assumptions of equivariance. Because when you take a look at the x-axis from 0 to 1 or 1.5, more or less clustered. You know what I mean by clustered? The distance from all those points to each other is not very much pronounced. But when you take a look from 2 to 4, what happened? They are dispersed. That means there is no equality of dispersion. And that was why we said assumptions of constant variance is violated. That's all we mean. Read it from the graph. Take a look at this guy now. That is the way the residual, if you take a look at what I have now, okay, when the residual plot look like that, like a wave, that's a pattern. A wave is a pattern. When residual plots as a pattern, you know what happened? Violation of linearity. Take a look at that. The other graph is violation of linearity. This guy here is a violation of equivariance. Take a look at it too. Okay? So the violation, but if you look at that of the linearity, okay? If you look at the other one, that of linearity, because it has a pattern. Okay? Residual plot should not have a pattern. If the residual plot has a pattern, that violates linearity. Okay? So take a look at that. Now, the next thing we want to talk about now is the unusual observation. I'm still going to walk you through how we investigate what kind of plots that we're going to use to investigate assumptions of normality. Okay? We call it QQ plots, normal QQ plot, but I'm still coming to that. But what I want to do now, I quickly want to walk you through unusual observations. An observation, if you take a look at that, there's something that we call an outlier. I told you, according to Benkamp in 1982, an outlier is a data point that is not consistent with the rest. And that is when we have an observation with an extreme y value. You have a y, you have a x, and you notice in your dependent variable y, there's a data point that is not consistent with the rest. Okay? And that is what we actually mean. But what about when we have an extreme value in x? Don't forget, when you are seeking relationship, you're seeking relationship between y and x, right? Y dependent, x independent. I told you the other time, y may represent the volume of sales. X may represent the amount you spend advertising. What if there's an extreme value in the amount you spend advertising? That's going to be called high leverage. So whether high leverage or outlier, they are unusual observations. And I showed you the other time in the graph. Okay, and let me tell you this. A high leverage point has potential to influence the feeder regression model. Oh my God, there's a lot, in the past, researchers have obtained a feeder regression model that mislead. Why? Because maybe the researcher failed to investigate unusual observation. If there is an unusual observation, okay, like either outlier or high leverage, that could change the decision. Okay. Now, and of course, we have a way to compute that, which my TA is going to show you that now. Okay, the HII, okay, it's 1 over n plus that, which I'm going to walk you through all of that. Now, you know what I want to do now? Distinguishing or making a distinction between an outlier and an high leverage. What I want to display now, there's possibility in your data set, you could have an outlier, or you could have a high leverage. You could even have the combination of the two. Now let's take a look at this. This guy is okay, right? If you take a look at this kind of plot, right? That's okay. Let us add this one. If you take a look at the second one now, what is happening with this adding an high leverage that is not an outlier? If you look at the second one, do you see the high leverage point? Do you see that point, right? That is far away from others. You see that guy, right? That is not an outlier. You know why it is not an outlier? Because it falls on the straight line with the rest. It is not an outlier, but it's an high leverage. Does that make sense now? If a data point fall on the straight line, on the same line with the rest, except that it is far away from others, it is not an outlier, but an high leverage. Let's take a look at another one. Oh my God, take a look at the second one. It is not on the straight line with the others. That's an outlier. So when you are working, characterizing relationship between two variables, you need to be able to investigate this. And that is why, why you need to draw. That's why you need to get all these plots. This plot will enable you to know whether there's a violation or not. But let me tell you this. It is not all outliers that can cause problem. It is not all high leverage that can cause problem. So I'm actually going to walk you through how we can investigate that, whether a particular outlier is basically going to change the decision of a model or not. Maybe police pull somebody over, right? It is not before a police can pull somebody over, the police has suspected something. But it is not every driver that was pulled over that gets ticketed or punished at the end of the day. I remember when I drove to Chicago like last month, in May, when I get to Wisconsin, the police pulled me over. And they asked questions if I were laughing and talking. And that was it. That is the end of it. I know she suspected, my children came out of the car and they wanted to use the bathroom. Of course, there's no bathroom on the highway, so I have to park for them to. And I put on the hazard, right? And I forgot, and I was in the fast lane. That the hazard was still on. That means he suspected something. What's going on? Something is wrong. So what I'm trying to say is that when there's an outlier or an high leverage, okay, we need to first detect that, and after detect that, then we have a way to investigate whether they could be detrimental to the model. Now I want to show you now. Oh my God, this is a double tragedy. If you take a look at the second one, okay, there's an outlier, and that very outlier is also a high leverage. Take a look at that. So if you take a look at all this, these are scatter plots. And that is where you're going to start from when you are trying to characterize relationship. Now, we will now want to talk about measures for detecting outliers now. Before police is going to pull somebody over, police must have suspected something. Before you'll be able to know how to deal with an outlier, you need to first have a measure to detect outlier. What are these measures? That's what I want to talk about now. Oh, this of your like, can somebody say confirm if you're seeing me clearly? This of your like, can you see hear me by talking?
Yes.
Thank you so much, and thank for confirming that. Now, number one measure is what we call residual. Of course, I walk you through residual. What is residual? Residual is the difference between the actual values of observation minus the predicted value. What am I talking about? Y minus Y cap. Okay? y minus y cap. That is residual, right? Which is the distance between, okay, the distance between what happened in reality and what your model predicts. And that was why we call the actual and predicted. Okay, actual and predicted. The predicted value, the actual value. Okay, so this is the residual. Don't forget that. E cap. Okay, so if I want to have a measure, so which means large residual may implies what? The presence of outlier or unusual observation. Another way to measure that is when I look at the standardized residual. Okay, the standardized residual is that EI cap, which is the residual itself, divided by sigma, the square root of 1 minus HII. Don't forget, what was my HII? I think I showed you my HII the other time. Yep, that's my HII. You see my HII. N is the number of observation. X is the independent variable. X bar, the mean of the independent variable. X is the sum of square. X is sum, is this. That is sum of square for X. That's what you mean. That is what you see as SSX. Take a look at that. Okay. Now, this is the residual plot that I talk about. Okay. And of course, you can see the variance of the variance of the residual. The variance of the residual is sigma squared into 1 minus HII. I think I just showed you what the HII actually means. The first plot is the residual plot, and the second one is the standardized one. What I'm just trying to show you here is the graphical representation of the two measures for detecting outlier. But let me tell you, these are old-fashioned. I'm going to show you the hybrid one. Before coming to the United States, I've heard about somebody called this guy. Do you know what? This guy is known everywhere in the world. This is a professor at the School of Statistics, University of Minnesota. So this guy, Professor Dennis Cook, puts forward a measure that can adequately detect an outlier in a data set, and it's not anywhere in the world. It provided a threshold. Take a look at that. You know what this guy did? Look at DI, RI squared, which means this guy is using the combination of what we have before. Take a look at that. RI from the standardized residual, and the HII, you're going to see HII from, I'm going to show you the HII. Now, the HII here, and this guy came out with some formula. We call that Cook distance, which I'm going to show you now. You see that? That very D, that's a Cook distance. Okay, we're actually going to compute that, and he actually created a threshold. And you know what this guy said? He said, and I quote, he said, the large Cook distance means that the observation is more influential. And what is the threshold? And he said, investigate cases with Cook distance greater than 1. When a Cook distance is greater than 1, that will influence the decision. But when the Cook distance is less than 1, that's no problem. Okay? Now, I want you to take a look at this. We compute the Cook distance. The Cook distance was 0.03, even though there is a high leverage, but it is not enough to change the trajectory of results. I told you the other time. It is not all high leverage or outlier that could be problematic. And how am I going to know whether it's problematic or not? I need to compute the Cook distance. When the Cook distance is greater than 1, there's a problem. When it's less than 1, there's no problem. Take a look at another one, like this guy now. We're suspecting an outlier because that particular data point does not fall on a straight line. It's not consistent with the rest, but the Cook distance actually came out as 0.41. That's no problem, but I'm going to show you, oh my God, take a look at this. The D is 4.7, far greater than 1. This is problematic. Does that make sense to you now? The police have pulled somebody over and the police realize this guy commits an offense. Therefore, he needs to be arrested because it's a risk to the society. That's what it means here. Take a look at that. Because we got a threshold. The threshold there is greater than 1. Now, what are go ahead.
What does the value HII represent in that code distance form?
No, they call it like at. At is going to come in an at matrix form. You're still going to do that in the lab. You know, I show you the formula, right? The HII is here. You can compute it from here. I'm going to show you now. You see that? When you have your data, and it's the number of observation, of course, you can, but by TA, we actually walk you through that in the lab, you know? That is the essence of the lab. That's a very good question. Okay, I quickly want to go to the next. Now, if you have identified outlier or high leverage, how do we deal with it? Strategies for dealing with influential observation. You know, some researchers, they've argued that they will simply remove it. But you know what? I argue about this in my PhD work. You cannot remove it. The only way you can remove it is when it's an error. Maybe you wanted to write 5 and you write 5,000. That's an error. You can remove that. What of if it is a genuine observation? And let me tell you my argument. If I conduct a test in this class, and maybe I have 10 students in a class, 9 students score above 90%, and somebody scores 0. If I want to compute a class average, am I going to exclude the person? Is it not a member of my class? He is a member of my class. So that is not an error. That's a genuine observation. So if it is a genuine observation, you cannot remove it. When you remove it, then you have altered your data set. Does that make sense to you now? We have a strategy to deal with that. Okay. And the way to deal with that is to fit a different model. And I call it a robust model. Okay. Then and that was why whether to remove or to use a different model, then you need to be able to understand what causes that outlier. If it is error, if it's maybe just an error in imputation, you can remove that. If it is not, then you need to fit a different model. Okay, my TA is going to walk you through this. This is a data set. Okay, so when this is a data set, as you can see, give me 1 second. So when this is a data set, take a look at what I have. Okay, if you look at observation number 21 for Y and for X, that number doesn't look consistent with the rest. If you take a look at that. Now let's take a look at that. We generate scatter plot. That is what we're going to do first, right? When you are seeking relationship. And you can see that red, right? It's not consistent with the rest, right? Let's take a look at that. Now, this is the coding now. If you copy all of that, okay, that you're going to have that, right? When you have this guy now, okay, you're going to do the diagnostics. If you want to look at it in terms of residual, I told you the other time, measures that we actually use is for detecting unusual observation we use residual, standardized residual, or you go with the cook distance, right? Now, take a look at that. Recede, 16.89. That's a very large one. Look at the standardized recede, 3.68. That's a very large one because the standardized recede, we expect something between a -3 and a 3, 3 sigma. Has anybody heard about 3 sigma? But this guy is more than 3 sigma, which means we have a large residual here, right? Now, let's continue to go with our code. Okay. When I do recede, and I try to recede is like getting the error, the predicted error for each observation. You can see the one in red. Oh my God, the one in red, 16 point something. That is far more than every other one, every other point. Take a look at that. Now take a look at this guy now. Uh, the arrow code for the standardized residual, which is the second measure. What happened? You can see out of 21 observation for residual, the one that is actually outside -3 and 3, the standardized residual is -3 and 3. If you fall within, if observation fall within -3 and 3, there's no problem. Even though there's an outlier, it may not be influential. But right now, take a look at this guy now. The observation number 21 is actually having a residual that doesn't fall within. Now I decided to go for cook distance. This is a code for cook distance now. It's going to be cooks.distance module. Where do I get module? Look at the module. The module is module equal to LM. Okay, now if I want to fit linear regression, it's going to be module equal LM into Y on X. I told you, you're going to write the dependent variable first before you write the independent. Take a look at that. Okay, so let's look at the cook distance. We program the cook distance. You can see 3 times mean. Okay, the cook distance is also using that idea. What does it give us? It's trying to say observation number 21 is influential. That's what it's telling us now. The influential one is that very one. Take a look at that. Now, the next thing now is, why should we care about outliers? If you want to know whether we should care about outliers or not, you know what we can do? Let us run a data set with outlier and without outlier, and let us compare. That is the only way to do. Take a look at this. Regressing Y on X using the data set without the outlier. Maybe you remove that. Why do you remove it? Maybe you realize that maybe there's an error in imputation. That's why you remove that. Now, when we just look at what is the beta note? 1.73. What is the beta one? 5.117. What was the R squared? 97.32%. We're still coming back to that. R squared is what we call coefficient of determination. It tells us how much percentage variation in the response in the dependent variable the model was able to explain. Okay, so we're still coming to all of that. Now, with outlier, what happened? With outlier, what happened? The beta naught has changed from 1.73 to 2.96. What about the slope? From 5.117 to 5.037. What about the R squared? Let me tell you, the R squared means coefficient of determination. If I want to know how good is a model, okay, we can look at the R squared or adjusted R squared in a situation where the dependent variable is more than 3. But right now, we only have one independent. We can still trust our R squared. The R squared without outlier is 97.32%. But with outlier, what happened to the R squared? R squared goes down. What does that mean? The quality of a model is reduced when an outlier is present. That's what it means. Because the R squared go down. With outlier, R squared is very high. Without outlier, R squared is very high. With outlier, R squared value gets reduced. Oh my God, that's going to be the head of the lecture today. I want to use this opportunity to entertain questions. Any question, whether in person or online? Any question? Just a few online. Can somebody confirm if you're still hearing me clearly? So everyone still hearing me clearly?
Yeah, I'm
Yes.
hearing you.
Oh, thank you so much. Thank you for confirming that.
I have a
This is the, oh, go ahead.
question.
Go ahead.
So for the page we're on now, how would you generate this with R?
Oh, you mean how do I generate which one with R?
Yeah, just for the output we're seeing right now for the model.
Oh, for what we're seeing now, how do we generate that with R? It's basically just going to be uh I'm going to show you now. It's just going to be where I have module. Do you see this guy?
Yeah.
You know, when you put module equal to lm into y on s and you do the summary, if you do the summary of the module, the summary into the module, it will generate, it's going to generate all these values for you. Okay, my TA is going to walk you through how you can actually get all of this in R. And the one you are seeing now that you see it as analysis of variance, okay, is just going to be ANOVA into module, which my TA is going to walk you through. That is the essence of the lab. Have I answered your question now?
Yeah, thanks.
You're welcome. Okay, so and that's why I need everyone to pay attention to the attendance of the lab is very crucial to discourse because you're basically going to be walk through how you can use a software to actually run our data set. You know, it's not something we can do manually because of the fact that our data set are voluminous. And that's why we actually need to have a way, that we can use to implement that and get our results on time. Okay, so attendance of the lab is very, very crucial. Now, uh, today I've actually walked you through how you can, you know, um, investigate, whether your model will do a great job or not. That's exactly what we've done today. And of course, what we're going to do next, give me 1 second. I'm just going to check my model. So it continues. Okay, it's a connection between what we've done, what we did today, and what we're going to be doing next. Now, what we want to do next, let me prepare your mind. We basically want to decompose our dependent variable. We want to be able to tell the world that even though there are 100% variation in the dependent variable, how can we decompose that into explained variation and the unexplained variation? Because it is not everything our model will explain. Our model is not perfect. And because of that, there will be the variation around the dependent variable will be decomposed into the variation that can be explained by the model and the one that cannot be explained by the model. And that's what we're going to do on tomorrow, on Tuesday. It's going to be the composition of the dependent variable. Okay, in the absence of question, this is where I believe somebody called Charles is talking, but it's muted, or it's just people talking in the background. I can see somebody talking and it's muted. Does the person want to ask question or is just a background talking? Okay, I think that's more or less a background talking. Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone.